This program is a presentation of UCTV for educational and non-commercial use only.
I come from a sort of pre-e-nabled era, but anyway, so we generate power in our business, and we're the folks that have homeowners lined up to plunk down $20,000 on a PV array for, most of whom probably wouldn't buy a compact fluorescent light. So there is a mismatch, if you will, and I'm going to try and address that mismatch today and see if we can come to a meeting of the minds. But my basic message is going to be that, that energy efficiency has got to be the cornerstone of what we're doing, that photovoltaics at the residence and small commercial level should be a part of that, and that there's a natural synergy between the two industries. And it's incumbent on all of us to figure out how to nurture that synergy. So I'm going to push a button here. Yeah. This, oh, by the way, this is some mumbo jumbo that our lawyers make us so since you've read and acknowledged, sign that you've read and acknowledged that, push return. I'll start out, though, with a little bit of history about SunPower, since this community may not be as familiar with us as more of a PV-oriented community. But the work was really funded initially by the utility industry and the U.S. Department of Energy. In fact, Southern California Edison became one of our sort of co-sponsors at EPRI. And this was back in a time when the vision for PV was going to be solar farms. Great giant things in the desert that would be generating huge amounts of power and shipping it to the cities. And we envisioned a sort of dish-type application back then. I actually got involved in building solar cells for such a dish, as you can see there. But the solar cells for that dish required very high efficiency, and it was out of that work that the high-performance solar cells were developed, but albeit for concentrator applications. That market never materialized. So SunPower became a sort of a boutique supplier of high-efficiency solar cells to anybody that could afford very expensive cells, like NASA, for example. And we built a solar-powered airplane array for them. But our big breakthrough, really, when we realized that the large central station market was a long time coming, was when we teamed up with Cypress Semiconductor. Cypress brought in a semiconductor manufacturing know-how to our technology. We married the two. They also, importantly, brought in $150 million to build a factory so that we could actually start making cells, standard cells. You see the picture on the right of our cell, which is unusual in that all the grids are on the back. We began production late in 2004 and IPO'd in 2005. We're headquartered in Silicon Valley. This is stuff that the CEO would normally be talking about, you know, manufacturing in the Philippines, highest performing solar electric systems worldwide. And our sort of positioning is that we like to deliver the most energy per unit of land or per unit of module area. We right now operate a lot of larger systems. We operate 500 systems totaling 400 megawatts around the world. We have a central control system in Richmond where we monitor the operation of all of those plants on a real-time basis. A big change for SunPower was when we merged with Powerlight Corporation. Powerlight was a leading system integrator building PV systems, mainly for commercial applications, flat roofs, had some dynamite technology in that regard, basically owned the market. We decided that it would be best to vertically integrate through the value chain to better understand the customer and to help the system integration aspect of the business reduce costs, which were sort of inherent in our sort of semiconductor background from the solar cell side. As a result of that, we've had some pretty dramatic growth with starting with production in 2005, really, and as you can see. So enough about that. We're kind of involved in all of the major photovoltaic applications except for watches and calculators and small consumer items. And we divide those into the 4 sectors shown here: the residential retrofit, upper left-hand corner; new home production, where we have a product that integrates in with the actual roof material, and it improves one of the barriers to consumer acceptance, which is appearance of the array. In the lower left is commercial building roofs. That's the Microsoft campus in Mountain View. And finally, the original vision was the large power plants, and those are now starting to emerge as a viable photovoltaic market. We have a bunch of product families, the flat systems for commercial roofs, the sun tiles for the new home construction, and the tracking systems shown at the bottom are for large power plants, where we track the sun throughout the day to harvest more energy. One of the things that was kind of interesting was that when we first started producing panels for residential roofs, because we had all the grids on the back, a technical feature which was done for purely efficiency reasons by us engineers, the panel ended up being quite better looking than a standard panel, and I'm sort of embarrassed to say that probably more than half of the consumer acceptance drive for SunPower has been because the panels look better. And as a result, we have the largest number of California residences in just a few short years. As I said, we kind of specialize in efficiency. We think efficiency is a key parameter in this whole space, and now I'm talking about not energy efficiency, but the conversion efficiency of the panel itself. And this sort of illustrates that, where we have a commercial application, a flat roof. It shows what SunPower is able to do in one application with 628 kilowatts of generating power on that commercial building. If we had used conventional silicon panels, it would have been about 410, and if we'd used thin film panels, about 204. So this sort of ability to drive larger generation on a given footprint of real estate is going to be sort of a feature as we try and see how energy efficiency and solar generation merge together to sort of inexorably move us towards the goal of zero energy buildings, which is the goal here. One of the reasons we merged with Powerlight is that we found that fully half the cost of a PV system was after you make the module. And that was where a lot of the low-hanging fruit in bringing the cost of PV systems down was located. So let me just briefly just show some applications to sort of flesh out what these market segments look like. This is a residential roof. This is a Sunset home. Demonstration home to show what you could do with energy efficiency and LEED type construction practices. This is a picture of the new home construction. We have a 650 home project near Sacramento. This is one of those. This shows a commercial roof. And this is covered with PV, typical application. And another commercial roof. This is one slide I generally show when I'm talking to politicians. That's the roof of the Department of Energy building in Washington, D.C. And finally, lots of distributed ground-mounted systems. These are sort of small power plants in the 10 to 30 megawatt size range that are ground-mounted, not roof-mounted, but located generally closer to load centers. so that you get some advantage of not having to go on to long-distance transmission systems. There was an explosion of construction in Spain last year, and some of these are power plants that we built in Spain. Finally, the most amazing thing, I think, to casual observers of the PV industry has been the recent emergence of the large, almost central station-like PV plant as a cost-effective entity. We recently signed a 250 megawatt agreement with PG&E. Another company signed a 550 megawatt agreement with PG&E. So these are things that are happening. We signed an agreement with 35 megawatt agreement with Florida Power and Light, and I think this was the first time that a utility actually rate-based a large PV plant. They did not enter into a power purchase agreement. They bought the plant. And they bought the plant because they felt it was a cost-effective addition to their generation mix, given the other options that they were facing for adding peak power. So that the climate has really changed. Now, I'm not here to talk about large power plants, so this will be my last picture of a large power plant. But rather, let's look at the spectrum of PV. So starting on the left is kind of very small systems located on people's roofs. The next one over is a commercial building. The interesting thing about the commercial building is that it generates, you can put PV on the roof of a commercial building, it's very cost effective, but it doesn't generate enough energy to cover the load of the building generally. Okay, just a fraction of the load is available. On residences, you can often cover the entire building load on an annual basis. The next one over is a new emerging market. This is a large warehouse roof where the warehouse itself doesn't really consume much power. So this is kind of like a power plant on somebody's roof. They're sort of loaning you their roof. They wouldn't be eligible for rebates under the current rate structure because they generate more power than they need. So it's maybe utility owned. But this is now an emerging sector in the business. And then I have the distributed ground mounted, and finally the large commercial power plant. So that's kind of the spectrum from small to big of what's happening in PV. And if you look at it, it kind of spans from a very distributed distributed energy model, to a very central station model. The interesting thing is that we find that PV is sort of equally well positioned along this value chain. And the reason is that at the very distributed model, we have higher cost of sales, higher installation cost, higher design cost. So the system's more expensive than a very large system, but the value of the energy is higher. On the other hand, with a very large system, we garner huge economies of scale, but we're selling much more into a sort of wholesale market. The value of the energy is lower in the middle of the desert. And those two kind of balance each other out. So we have an industry that's sort of feeling its way along this entire value chain, where the sweet spots are between the residents all the way up through the commercial and the large power plant. And there's no clear best place yet along that value chain. So it's an exciting time, a lot of activity going on there. If you step back, though, and look at it from the perspective of the grid, as a technical entity or energy supply system, you really should think of the small systems as more like efficiency and the large systems more like generation, at least in my view. And the reason is that at the home level, for example, the grid really doesn't care too much whether you bought a new, more efficient air conditioner or put PV on there, right? I mean, you know, in both cases, you reduce the load something, right? And so it is like an efficiency measure, if you will. On the other hand, clearly a giant power plant in the desert is a generator, albeit one with a lot of problems associated with it because it kind of generates when it wants, not when you want. But this is sort of what's happening. So if you look at it, there's a synergy between energy efficiency and PV, kind of at the low end of this market, basically, right? So where we're going in and sort of reducing building loads. In other words, there's an efficiency where we're trying to head toward, there's a synergy where we're trying to head towards zero energy buildings and zero energy homes. And that's sort of the crux of where I'm going to focus the rest of my talk. If you go into a building and you look at what you can do to reduce the building load, there's a bunch of options that you might have. You might be able to put new energy efficient lighting in, HVAC upgrade, improved controls. You can put PV on, that reduces the building load. And there's other things too. And each of these has a sort of a different return on investment profile. Now, each application is completely different. I don't mean to imply that every case is going to look exactly like this, but the message is that as you put in efficiency upgrades, some pay back shorter, some pay back a little bit longer, and you have this whole hierarchy as you march down the curve there. But one message that I do want to show is, and I'll show you some case studies later on, is that on the bottom axis, the total energy delivered or saved by the particular investment, generally PV you can do the most. So I show here, of all of the options available to sort of head this building in the direction of zero energy, PV is the biggest energy chunk available. It's not the cheapest, but it's the biggest, okay? And notice that I made the vertical axis return on investment. One thing that we have to help customers understand is oftentimes they'll come in with a simple payback idea. You know, well, this thing why should I put PV on the roof when I can do blah, blah, and it pays back in a year? And it may be that that's a better investment, but simple payback's not the way you should look at it, because a lot of these upgrades have fairly short lifespans. PV has quite a long lifespan. You can finance it for 25 or 30 years. So you really have to get out of this simple payback mindset and start helping the customer with the return on investment. And each customer has a sort of ROI hurdle rate that they're willing to deal with. They have money available, they want to invest, and they expect a certain minimum return. And clearly, they're only going to do those things that are above their return on investment hurdle rate. Okay, so some things might get left off the table that they would normally like to do. But it's not quite so simple as that because of the financing options. So one of the nice things about PV when you go to a customer is they're so imminently financeable. With a power purchase agreement, for example, they have a nice long life. You can enter into a power purchase agreement. It doesn't take any of your own capital, and you can suffer benefit immediately from a reduced energy bill. And the reason that is because the system is not owned by you, right? And so the financier, if you stop paying your electric bill, he can come and get his PV array, in principle. I don't know if that's ever actually happened. But that's different than insulation, for example, where you're not going to expect, if you don't pay, that the contractor is going to come and tear out your insulation. Right? So it's a different financing kind of thing. That may have to be done under a completely different budget in a company. Some of these things might be done under capital leases. So you have this sort of spectrum of financing options available. But one of the things that's made PV so easy to sell is imminent financeability. Okay. In addition, it's easy to tell if it works or not. Whereas some energy efficiency measures, that's less so. And I'll talk a little bit about some of the things issues that causes and what we're doing about it. So that brings up the question, why do you want to combine energy efficiency and PV or solar? Well, I mean, I don't know, these numbers are sort of given to me by a sales team or something. But fundamentally, I think it's all heading towards that bottom one, which is everybody wants to go to energy efficient designs, LEED buildings, try to drive towards zero energy buildings. And you can't do it with either one alone, as you'll see. Very, very difficult. You need them both. They've got to work together. By working together, you can often leverage your cost of sales and that sort of thing into a bigger project and garner savings there. And then you have all the sort of the nice things, electric rate hedging, and that sort of thing in the future. So this just shows a typical, this is also obviously just a sales slide, but it shows the load profile on the left there during a day, electric power profile for some particular customer. And it peaks up during the center of the day because of air conditioning load. With solar added on, you can kind of go to that lower bottom there. You can pick up about half in this particular application. And then with energy efficiency, you can move that bar down even further. So on the right, the numbers for this particular application where the customer was spending $100.60 a square foot per year on electric bills. With solar, he was able to decrease that to $1.20 per square foot with PV, and with energy efficiency, bring that all the way down to 95 cents per square foot. And this slide sort of captures some of those, those synergies, if you will. This is actual numbers here. So one of the projects that we did was with Macys, I think 27 stores, and so we have a lot of data. And this shows the overall result for that project. Macys was spending $1.85 per square foot per year on energy. The solar system that we installed on average for all their stores brought that down to $1.55. And the energy efficiency improvements that were put in place alongside of that brought that down to $1.15. In this case, the energy efficiency improvements were larger than the solar, but they don't always vary. But in any case, we were able to reduce Macys' building load 43% with this combination, a substantial improvement. And a typical sort of project financing looks something like this. For a typical store, the system might be 1.1 megawatts. The customer enters into a 20-year power purchase agreement. We go in and put in new lighting, efficient lighting, new up-to-date HVAC, variable speed drives, energy control systems into the building. The energy efficiency part is generally financed with a capital lease, and the solar part with a power purchase agreement. So some bank owns the system, basically. The annual electric cost for that building was $1.35 million. Prior to doing all this, they were paying on average 13.7 cents a kilowatt hour. And the bottom line was the following. With the PV on the roof, we saved them 1.4 million kilowatt hours. The energy efficiency improvements were 800,000 kilowatt hours for 2.2 million kilowatt hours total saves. Shows a cumulative. But the bottom line is that the net present value of all these projects is positive, which is, the hurdle, if you will, at their discount rate. Actually quite positive. And the energy costs are substantially reduced. Macys went, in this particular building, from 13 cents a kilowatt hour to 10.6 with these improvements. So there's this interesting synergy that goes on there. This just kind of reiterates some of that. But what we find is when selling energy efficiency improvements, one of the big hurdles is you're selling something that doesn't really exist, right? You're selling negawatts, and it's hard to measure negawatts. If the building consumption goes down, the owner of the building isn't sure, well, did they turn off an air conditioner? Did they unplug something? Were people more conscientious about lights being dimmed? Was it hotter or cooler during that period? So one of the things we've done is we've put together a modeling program to help customers model their entire building energy flows, and with inputs like weather, outside temperature, solar insulation, wind speed, and that sort of thing. And that allows them to do a baseline on their building and extend that out so that in the future, if they didn't do anything and their energy consumption went up or down, they could pinpoint why. Was it sunnier, hotter, whatever. And when we do put the system in, if the energy goes down, we have something to compare it with. So the building owner has something concrete to say, yes, my investment did do something. And this shows Macys Irvine store. So the blue line was the baseline we established for them. And that's what it should have, that's the energy consumption they should have had if they didn't do anything. The little vertical bars are actually, this is actually just after installing new lighting in this case. The little vertical bars are the actual energy consumption that would have happened given the conditions that were prevalent on that day, because it ended up being a hotter year than expected. And the red bar is the actual building energy load. So the customer can look at that and say, yes, we have done something, our energy has gone down. But every situation is completely different. This shows a case of a winery where there's not as much opportunity for energy efficiency. In this case, the load profile is shown. And with PV, we were able to get the bulk of that peak out in the middle of the day and take out a lot of the energy consumption in the building during the day. But with energy efficiency, which is the little orange part down below, not so much. Okay. Just another example. But they did suffer a 50% reduction in annual electric bill from the combined aspect of PV and energy efficiency measures in that case. This shows another winery, which we did a little bit more in. We put new lighting systems in and better control system. And it shows the efficiency improvements, the load reduction improvements that were garnered there. Once again, the PV was the bulk of it. But notice that it really smoothed out the energy consumption from that building. It kind of pretty much creamed off the midday peak of energy for the St. Francis Winery. We've done a lot of these things. We did the Moscone Center in San Francisco, where we put in lighting also and work with the convention center to improve the appearance of the booth area and the convention areas while dramatically reducing their power consumption. So I think there is, in fact, lots of reasons for the communities to work together, and I challenge you to do that. We certainly will reach out to the energy efficiency community as much as we can, because I think there's a lot to be done as we march together towards this idea of zero energy buildings. So with that, I'll say thank you and take any questions.